Hey there, Calc folks, back here with another video in our study of the derivative, where this time around I want to look at the case for derivatives of the sine and cosine function. Right? We're going to look at the case of finding the derivatives for our two fundamental trigonometric behaviors, the case for the sine and the cosine. Right? So let me bring up the notes here, folks. Here's our notes. We're going to be looking at sine and cosine rules for derivatives. And again, we're just going to be finding those two very specific cases of derivatives. The derivative dy dx for y equals sine x, and the derivative dy dx for the case of cosine x. These two most fundamental trigonometric behaviors. And I will tell you, if we can find these two, as with what we understand from trigonometry, is that if we have a little knowledge of sine and cosine, we can use that knowledge to make statements about tangent, cotangent, secant, and cosecant. And that's what we're going to see occur in our next video, folks. We're going to go a little further and look at the other four trig functions after we develop these results for sine and cosine. All right. Now, I do believe I jump right into the proof here. Well, first of all, I give you the results. For the case of the sine and cosine functions, their derivatives, right, are themselves trigonometric functions. And what we see interesting enough here is that when we think about the derivative of the sine function, well, it's simply described by the cosine function. And when we consider the derivative of the cosine function, it's described by what we would say is the opposite of the sine. All right. The derivative for the sine and cosine functions have two pretty unique results here, in the fact that they are just variations of each other. The derivative of sine is cosine. The derivative of cosine is opposite sine. Let's look at a little proof of why that is. We start with the proof of the sine. If we let f of x equal the sine of x, right, then we know from the definition of a derivative function that f prime of x equal to the limit as h heads to 0 for f of x plus h minus f of x all divided by h. In the case of the sine function, would produce the limit as h heads to 0 for the sine of x plus h minus the sine of x all divided by h. Where we can say something about the sine of x plus h. All right? If you go back to your trigonometry and recall, all right, we have there the sine for the sum of two angles, the angle x and the angle h. And recall from trigonometry, the sine of x plus h, right, it can be thought of as the sine of x times the cosine of h plus the cosine of x times the sine of h. Right? That was our trig identity for the sine of two angles, angle x and angle h in this case. The sine for the sum of two angles. Recall, this is our trigonometric result for that sum, that sine of the sum. If we now substitute the result back into this statement for the sine of x plus h, we can see that our statement for f prime is going to transform into this statement seen here. What's going to be the limit as h heads to 0 for the sine of x times the cosine of h, plus the cosine of x times the sine of h, all minus the sine of x divided by h. Right? Substituting in for this sine of x plus h, this result we recall from trigonometry. Now, in this variation, what we can see is we can now organize this ratio into the following statement. We can group the sine x cosine at h with the negative sine x in our first group and divide that by that common denominator of h. And add to it in our second group this factor in the middle, cosine, or this term in the middle, the cosine x sine h. Right? If we group that as such and we consider the behavior for this limit now, this limit is going to distribute itself to both of these groups. And in the first group, you're going to have a common factor of the sine x. And in the second group, you're going to have a constant multiple given by the cosine x. And that common factor of the sine x can actually be factored out of this first group. And in fact, we might even add another line here. Let me hold on here. Copy this line, bring this down. And let's drop it in here, where what we'll highlight is we're going to factor out a sine of x from this first group. And that will move out in front here. And from this group, we're going to factor out a cosine x. Right? Now that sine x and that cosine x, when we distribute this limit across this summation to this term and then to this term, that sine x and cosine x are going to be constant multiples. And they can be factored out of those limit operations as we see here. Right? We can see here we have the sine x times the limit as h heads to 0 for the cosine of h minus 1. And we're adding to that the cosine of x times the limit as h heads to 0 for the sine of h divided by h. With the sine x being factored out of this first limit statement and the cosine of x being factored out of the second. And we can factor them out because they do not involve the variable of h in their calculation. Only these second groups involve the value of h. Now you might recognize those limits. Back when we were introducing limits involving indeterminate forms, we had mentioned this scenario and these two cases for limits. We said these are unique cases of trigonometric limits, where the limit as h heads to 0 for the cosine h minus 1 divided by h is equivalent to 0. And we had shown that the limit as h heads to 0 for the sine of h divided by h is all equal to the value of 1. And we can substitute those results in for this case being 0 and for this limit here being the value of 1. And when we think about the f value of f prime of x, right, substituting in here for the value of 0 and here for the value of 1, we have the sine x times 0 plus the cosine x times 1, which is really just 0 plus the cosine x, or in the end, just the result of the cosine. Thus, the derivative of the sine function with respect to x is just the cosine function, as we've proven above. As for the derivative of the cosine, let's take note. As for proving the derivative of the cosine, let's separate this. All right. What we rely upon is what? Is that idea that the cosine of x is just a shift left of the sine function pi over 2 units. And when we think about the cosine of x, it really is simply the sine of x plus pi over 2. Again, this is another trig identity. This is the phase shift identity, where the cosine of x is sine of x plus pi over 2, or I believe we say the sine of x is the cosine of x minus pi over 2. All right. Where if I substitute that in for the cosine of x into my derivative argument, and we say the derivative of the cosine is equal to the derivative of the sine at x plus pi over 2, I can then use chain rule on the statement involving the sine of x plus pi over 2. Right? Setting that up with a little bit of chain rule where we say this is going to be f times, or f evaluated at the quantity g of x. G of x is going to be the interior, that linear statement x plus pi over 2, and f is going to be the exterior function given by the sine. And if we find their individual derivatives, right, if we think about f of x equaling the sine x and g of x equaling x plus pi over 2, from this setup, we can then say that f prime is going to be the cosine of x, right, because f is the sine. So f prime is going to be the cosine. Now remember, in the chain rule, we are going to substitute back into f prime the value of g of x. So f prime at g of x is going to be the cosine of x plus pi over 2. As we had said, if we shift right pi over 2, we would be the sine x. But if we shift left pi over 2 for the cosine, we will shift, or we will become the opposite of the sine function, negative sine x. And then lastly, g prime of x would just be equal to the value of 1. Right? For that linear form, x plus pi over 2. Right? Its derivative will just result in 1. So it's going to be 1 times negative sine x is going to be our result from chain rule. And 1 times negative sine x is itself just negative sine x. So if we think about the derivative with respect to x for cosine x, following from some chain rule setup, all of this is equivalent to 1 times negative sine x, which gives us negative sine x as the result. And thus the derivative with respect to x for cosine x equals negative sine x. Right? That's proof of the cosine's result. Now, what do I look at next here? Oh, I look at a graph. I look at their graphical illustrations. Right. What's interesting here to look at with the graph of these two functions is how the slope of the sine is illustrated by the cosine. Right? Here I'm just showing you the illustration between f equals sine x and its derivative f prime equal to cosine x in the static graph. And you can see here, I place this point on the sines graph, the blue graph, right at the value of pi. And we can see the slope of the tangent line here would be this negative slope, and it would be described by the cosine's value at pi, which would be negative 1 in value. This slope is actually negative 1 in its rise over its run. It drops 1 when it runs to the right 1 unit. And notice that the slope of the line tangent to the blue graph is actually going to oscillate between positive and negative 1 as we move across the graph of the sine function. And its output, its slope, will be described by the oscillation seen in the cosine wave. And to help illustrate that, I do have a graph here that we can look at. Let's see if this will load up for us. Hopefully it hasn't unloaded. I think it's still live. Yes. So you can see here I've plotted the sine function in blue for what is a few periods here. I think this is 2 periods from 0 to 4 pi. That's over 2 periods is the sines graph. And what I have plotted next to the sines graph is the slope of the tangent line. As I move my slider here, that slope of the tangent line moves across the graph seen in blue, the sine function. And as we can see, as it moves across that graph of the sine function, it oscillates between the values of 1 and -1. Here at the end, it's +1. And let's go back to this end. As we start at the beginning, it's +1. And as we begin moving forward, it's going to become 0 here at the top of this peak. And then it's going to turn into -1 about halfway down and then level back out at 0. Right about there. And notice all of this is the output, the slope is all being described by this point that's traveling along the orange graph, which is the cosine wave. So yeah, I can see the slope of the line down here is 0, and we are on the cosine wave right there at the value of 0. When I move the slope of the tangent line to here at 0 for x along the sine wave, we'll be at our steepest slope of 1, seen up here on the cosine. Right? We can see that point, relatively speaking, on this graph. Right? Pretty close. And as we move from left to right across the graph, what we should see is that oscillation in the slopes. And this graph illustrates that oscillation in the slopes that's being described by the cosine wave. Right? The oscillation in the slope of the lines tangent to the sine wave in blue is described by the oscillation seen along the cosine wave in orange. Right? That's what this illustration is showing us. It is more of a dynamic illustration of this illustration that we have here in our notes. All right. Now, and I think I finished with an example. Just to bring this into play, we might consider finding the derivative with respect to x for the argument y equals the sine of 5x plus 9. Right. Well, from the chain rule, where dy dx is equal to dy du times du dx, we can let u be the interior function, that linear function 5x plus 9, which will end up implying that y would end up being the sine of u. Right? If I substitute in for the value of 5x plus 9 the value of u, we can see y is going to turn into the sine of u. Now with u equal to 5x plus 9, I can find the derivative of y with respect to u. That's just 5. And with y equal to the sine of u, I can find the derivative of y with respect to u, which is just the cosine of u. So from chain rule, this is version 2 of the chain rule, right? We've identified du dx is equal to 5. And we've identified that dy du is equal to cosine u, because we are looking at, let's set this up, the derivative with respect to x for that linear case for du dx. And here we're looking at the derivative with respect to x for just the sine of u, right? I'm looking at the value of dy du. And from the chain rule, dy dx then is just going to be the product of dy du with du dx. It is just going to be the product of these two end results. It's going to yield 5 cosine u. Where since u is equal to 5x plus 9, we can substitute that back in finally for the value of u and be able to say that dy du must be equal to 5 cosine of 5x plus 9. This all developing from a little bit of chain rule. Where in that chain rule, we do incorporate this derivative for the sine function. All right? It's derivative of sine and cosine functions, folks. They are interesting in their behavior, in the fact that one describes the other. All right? We can see that in the sine and cosine waves. the slope of the lines tangent to the blue graph are described by the orange graph, and the slope of the lines tangent to the orange graph would actually be described by the opposite of what would be the blue graph. If we reflected the blue graph around the x-axis, that graph would describe the slope of the lines tangent to the orange graph. That's interesting behavior with sine and cosine. All right. We can incorporate those results now into our other rules: product rule, quotient rule, sum and difference, chain rule, as we see here. These two results for the derivative of sine and cosine will be incorporated into now our work. And having a little bit of knowledge also about these two derivative results, that the derivative of sine is cosine and that the derivative of cosine is the opposite sign, we can use that to then begin developing our derivative rules for tangent, cotangent, secant, and cosecant. Because all those are ratios or quotients of sine with cosines and or reciprocals of sine or cosines, which are ratios of 1 over sine or 1 over cosine. And we'll be able to apply some of our developed techniques to actually develop those derivative rules for those remaining 4 trig functions. And we'll see that develop in the next set of notes, folks. All right? But that is the derivative rules for sine and cosine, their proof, and a little example. All right? And what we'll come back to is we'll see a little bit more use of these results in developing the 4 rules for tangent, cotangent, secant, and cosecant. All right? So, with that said, I will end this video, folks, and I will see you in the next one.